Hi guys, my name is Anil. A bit about me, I'm from India. I did my master's and bachelor's from India. After my master's, I worked as a research assistant in University of Lincoln, UK. In University of Lincoln, I primarily worked on IoT, which is Internet of Things based coverage optimization for wireless sensor nodes. The PhD topic I'm currently working on is pedestrian movement analysis in complex public spaces, with privacy as a prime concern. So I'm working under the Dr. Bianca, and my PhD is funded through DREA. The prime focus of my topic is how pedestrians interact with their surroundings, and does it have any effect on path selection and their destination. Because the current literature and current methods mostly focus on the flow. There are very few who focus on their behavior and how it will affect on their surroundings. So the topic which I am currently working on will try to analyze, does the surroundings has any effect on the path selection and their destination, and how they behave, does it have any effect on the path and the destination. And we should do all these with according to GDPR regulations. With GDPR introduction in 2018, the GDPR imposes strict regime what to process and how to process. Since, as you can see in the images, we mostly focus on people as the pedestrians, so which contains mostly sensitive information. So we have to have a focus on what information we need to process and how we need to process them. So before I'm going to the paper, I will talk a bit about GDPR and how it relates to the paper which I selected for this presentation. So when GDPR introduced in 2018, so video surveillance is defined as a high risk processing operation in the GDPR. And the GDPR regime itself states that there should be privacy safeguards to hide the originality, even to store and export the visual data. Okay, so that regime didn't specifically said anything about visual data, but it mostly talks about personal data. While we're processing any personal data, we shouldn't store and export the personal data. And when we're talking about visual data, which mostly images or video, it itself is sensitive, so it automatically applies to visual data itself. So the privacy principles is one is the default. It should not be accessible by any authorized people. This is one of the default one. It should be implemented irrespective of what data you're processing and how you're processing it. Whatever the data you process and whatever the data you possess, it should not be accessible by any unauthorized people. You can see there is a imposition on Twitter like 2 or 3 days ago in Irish GDPR data regulator or something, because there is some data leakage, unauthorized data leakage from Twitter. So by default it imposes that it should not be accessible by unauthorized people. So that's a step 2. The step 1 will be how we can protect the data by design. So in the principle it states that one is the minimization, another one is the pseudonymization. So the data minimization states that you should only collect what you need. You should only collect what you need, and you should only process. You should only collect and process what you need. You're not supposed to collect more than that. So pseudonymization is replacing the actual personal sensitive info with a pseudonym. So whatever the info you consider as the sensitive or comes under GDPR, it should be replaced with a pseudonym. So once you anonymize it with irreversible algorithm or which is automatically named as a pseudonym, it is out of scope for GDPR. So once you do that, the data, it can be stored anywhere for indefinite period of time without any GDPR compliance issue. So you can take a video, you can do some pseudonymization on the video for all the sensitive information on the video with, you can replace with a pseudonym. Then you can store it for infinite of time and you can process it as you wish, because it no longer comes under scope of GDPR regulation. So this view we're currently more focusing on. It might change on the long run, like after 1 year, 1.5 year. We are thinking it might not change, but this is the view we currently going in the project. So one of the pseudonymization methods for a video is video redaction methods. So as you can see in these images, these are 4 popular video redaction methods which is used for pseudonymization. So blurring, as you can see here, you can blur the faces or the sensitive information you can find on the image or video. Or this is a pixelation where they replace the pixel with some noise or something, and so you can't recognize the face or here. And the masking. And the masking is replacing the actual face with some cartoon character or something. The problem with these 3 is you can't get the features out of it. Once you do that, that is, of course it is irreversible, but you can't get any features out of it. Let's say you process a video, if you can't get any features out of it, it itself is useless. If you want to do some high level processing with that after a year or something, you can't obviously use that thing. So in these 4 methods, visible abstraction showing more promise, because it's to some extent it replaces the original features with the 3D model. Okay, so as you can see, the visual abstracted model is not exactly replacing the virtual image, but it is somehow equal, or it is the parameters, whatever the features virtual image processing is somehow replicated with the visual abstraction. So let's talk about visual abstraction. So what are the current models available for visual abstraction is not expressive enough. As you can see here, it is not good enough, it's not expressive enough. So we need a better model for that. And when I'm talking about pedestrians, pedestrians and their behavior, we are mostly focused on 2D pose and 3D pose. Okay. The problem with the 2D pose, these are the key points, and key points are joined with the skeleton model, and this is a 3D model for the skeleton model. Okay. The problem with these is these are not sufficient to represent the gestures. As you can see here, you can see the hand, it is not properly represented in any of these models. So the joints alone are not sufficient to represent gestures, and they are not obviously good enough for behavioral model. So we need a better model for it. So the paper, which is the prime focus of this presentation, is expressive body capture, 3D hands, face and body from a single image. So in this paper, the author tried to model a person in an image. They take a monocular image and they make a 3D model out of it by replacing the shape and pose with the hands, body and facial expressions, all with a single image. So the way the author put in the paper is, to do that, to get the 3D model out of this image, we need 2 things. We need a model which is able to represent the complex the complexity of human body, including face, hands, and body pose. And we need to find a way to extract such a model from an image. So once we have the model, and we can turn the model, or we can pose it in a such a way. So the model should consist of a pose and the shape. As you can see, it should replicate the pose, and the shape of the body. The previous approaches of modeling a body using modeling a 3D body, they try to model each part separately. As you can see further in this presentation, there are some three data sets which only contains the head, body, or hands. Okay, so instead of that, the author tried to make a unified model. Okay, unified model which having a head, body, and hands. Okay, so the model is vertex Boson model with a linear blend shapes, and it has a 10,475 vertices. It has a property of 10,475 vertices with 54 joints. I will see why these 54 important in the next in the presentation, because these 54 joints are much different with the other 2D or 3D joints available, which are focused on the literature. Okay, so the model itself is defined as a function of pose, shape itself includes body, face, and hand, and facial parameters, and each is represented in a 3-dimension. So to train a SMPLX body model, which is a 3D model, they use different data sets. As you can see here, it consists of a pose and shape parameters plus facial expression parameters. Okay, so they use a different data set for each of those parameters. They take a Caesar dataset, which has a 3800 models in a pose capturing variations across data. So the Caesar dataset only has a single pose, but it has a multiple body shapes. Okay, so they try to capture a body shape across the Caesar dataset. Body shape, sorry, not pose. For the body pose parameters, they depend on a FAST dataset. It has a 1086 elements in a diverse pose. Okay, these are theta. Sorry, these are, I think, sorry, these are part of beta, I can say. This is beta p. This is body shape. And body pose parameters are from FAST dataset, and facial expressions they get from flame dataset, which is from same research group. And for hand, they use on the mono dataset. So from all these data sets, they try to get the principal components, and they make a unified model with a parameter of 119. So across different genders also. So for global body rotation, they take a 75 parameters, and for 24 hand pose, and 10 for subject shape, and 10 for facial expression. As you can see here, the shape is only represented in 10 parameters. Here, this plot represents the model shape space relative variance, the shape coefficients across different genders. This is the generic female and male plots. You can see it almost go to 1 when we are using 10 shape parameters, right? This is only for shape, and this plot represents the shape coefficients for entire model, for 119 model. Okay, so these are this represent in vertex to vertex mean absolute error. You can see here when we are getting around 119, you can see it almost flat, the curve is flat, so I think they take 119 parameters across different genders. And you can see here the pose parameters, the total pose parameters here are like 99. So 24 alone for hand pose and 75 for global body rotation. So once we have the model, so they just define a model with some parameters. You have the model. If you have the 119 parameters, you can make the model out of it. Then once you have the model, you need to pose it. You need to rotate the model according to the pose which is present in the image. So to do that, they defined a method named as SMPLify-X. So first they'll get a 2D pose from open pose. Open pose is widely used 2D point 2D joint 2D joint model. So it will just take an image and get the 2D joint positions. Once you have the 2D pose, then they will try to fit the SMPLX model, which is a 3D model, to the 2D features. Okay, which is done using pose pre-error. Once you've done that, then there will be correlation penalization and channel detector, which I will be explaining further in this video. Okay, so open pose uses a bottom-up approach. So first they will detect the key points for the persons in the image. Then they will map the key points. Then they will map the key points for each person. That's a bottom-up approach, right? So one of the key point here is open pose detects the key points for body, hands, face, and feet. Okay, the SMPLX model, which is currently released, doesn't model feet. It only models body, hands, and face. Okay, so fitting SMPLX model to image, they take it as optimization problem. So they have to minimize the error term. This error term they have to minimize it. By they have to minimize by optimizing this function actually. So where you can see theta b and theta f are pose vectors. These ones are pose vectors. E beta and these EMH, E alpha and E beta. E alpha, and there are certain E beta and E alpha. You can see here, these are for pose periods, and EJ is a joint based data term, which is used to project from 2D to 3D, which we will discuss in a bit. So as you can see here in the objective function, objective function can be divided into three phases. One is the data term, which is used to 2D giant reproduction into 3D, and 2D point reproduction into 3D into SMPL model. Then pose periods, which is used to correct the pose output pose from the projection. Then shape and expression pairs. So when we're talking about joint reprojection, it is trying to penalize the weighted true distance between joints and corresponding projected SMPL joints. As we've seen before, SMPL has 54 joints. Okay, they try to correspond these 54 joints to the open pose joints. I believe open pose has like 18 joints. I'm not sure those, but I think they come across 18. Yeah. Then there is a camera term which we don't know before, so they'll try to assign some camera term first. Then they try to optimize on the camera term by change. If the difference is too much, then they further change the camera term, then try to optimize it again. So they also introduced a weight term to reduce the edge noise, as you can see here. Pi k is a repression term. Then once we have that, once we have the 24 joints from 18 joints, then they apply the transformation which transform the joints along the kinematic tree according to pose. So once we projected joints, once we have the joints, then we need to transform them according to kinematic tree. So the 3D model pose will be same as the shape in the image. So that they do with the R function R. So once we have the pose, we either try to constrain the pose, because it is very much possible that the model may produce impossible poses. So they introduce a V poser using a variational encoder. So this variational encoder is trained on a 32 dimensional latent space, which is used to penalize the impossible poses while allowing the possible ones. Okay, so what they did is, so they will use this prior to get the 32 dimensional latent space, and they will optimize on this 32 bit dimensional space, then they transform back into angles. Okay, so as we can see, we have 99 joints, we have 99 pose parameters. Okay, instead of optimizing those 99 pose parameters, they will optimize the pose parameters on the 32 dimensional, then they transform back into 99. So this itself will improve the optimization, and also we are removing the impossible poses. So for the V poser, they use the CMU motion capture dataset and human 3.6 motion capture dataset. They extract the XMPL pose parameters. As you can see here, this is not SMPLX. Okay, this is SMPL. Sorry for I couldn't write it properly, but this is SMPLX. The model which the author discussed currently is SMPLX, but the V poser is trained using SMPL, which is from the same research group, but it is like a previous model. The SMPL is only targeted toward body pose. Okay, so they trained it using body pose, then they optimized it using body and hands. Okay, so these are the few sample poses from vPoser. As you can see, once the training is completed, it will describe the manifold of physically plausible human body poses. So if you give a 32 dimensional vector, it will produce one of the pose. Okay, these are the few samples of the poses which are available there, and it can also be used to efficient 2D to 3D lifting. So once we have the pose, then we need to adjust the shape according to the person which is present in the image. So for the body shape approximation, they use a primitive capsule approach. Okay, which is a very primitive approach, but it came as like it is it produced comparably good results. So they take a 20 capsules, one per body part. Okay, then they will perform the optimization to minimize the distance between capsule and body surface. Okay, so what they will do is they will take a capsules, and they will try to fit the coefficients to the axis length and radius of this capsule. So they will optimize this length and radius along the capsules, so the shape will be optimized for the given shape parameter. For the 10 push parameters we have, 10 shape parameters we have, so they will optimize these capsules on these parameters using a gradient based optimization method. So once optimized, it is very much possible that there will be collisions across the vertices. or triangular meshes. So they'll try to penalize these penetrations using a depth of the intrusions. Okay, they take the distance of these vertices, or then they'll calculate the intrusion of these body parts. Then they'll try to penalize the intrusions using the distance, and they're currently using a collision penalizer for that. And another feature for this simplify is they try to come up with a deep general classify using a 2D joints. The current Most of the current general classifiers are depends only on facial features. I think facial and body features. But what they did is they take the resonate 18 and they fine tune it using the dataset which are currently available, which are MS Coco and MBA and LSP datasets. And the classifier which they designed or they fine tune takes an image and 2D joints and assign table to the and they process it and assign a label to the detected person. So they validate the images using it to do joints. This is the part which they improved because they try to keep only images with a high confidence of head and torso and one for each limb. If the detected image only has a 2D joints has a good confidence, good detection confidence for head and torso and at least a limb, then only they taking that image and they classify it for a gender. If that's not possible, they'll just put it as a neutral. And for the optimization, they first make estimate of camera position. Just they place a body on the image, then they will just move the body around, so it will be the camera. So they move the body around, the global position will be same to the position on the body, position on the image, sorry. So once the camera is fixed, then they will try to optimize the pose, which is suits better for the 2D joints. Okay, I found a small video which which will have a bit more visual explanation for this process. I'll just play that here. Sorry, what happened? As you can see here, the optimization try to first place the body and they try to rotate the body, so it will just fix the camera first. Then once the camera is fixed, at this point actually once the camera is fixed, it will try to correct the pose of the body, 3D model actually, as you can see here. So it will do the same for the second one also. It will just first get the body, but the shape will be the same, because the shape will be done before the pose. So once the shape is fixed, then it will try to correct the camera, then the pose. Okay, that's it guys. Thank you. Please let me know if you guys have any doubts in the chat. Thank you.